Hi! In this video, we will discuss the basic concepts of stress and strain and how they are related. To understand the properties of different materials and how strong they are, a test, known as the tensile strength test, is performed under controlled conditions. During this test, a long specimen is pulled with force. The force that breaks the specimen depends on the area of the cross-section of the specimen and the type of material used to make it. If we divide the value of the force by the area of the cross-section of the specimen, or in other words, normalize the force by the area of the cross-section, a new quantity emerges. This quantity stays the same at the breaking point for each material with different areas for the cross-section. We call this quantity stress and define it as force divided by the area. We use the Greek letter sigma to show stress. The stress value that beaks the material is known as fracture stress. Thus far we can say that stress is a scalar variable that is similar to pressure. In fact, it has the exact same unit as pressure. P, S, I, and Pascal are the typical units used for stress. We also say this stress is normal stress as it is normal to the area of the cross-section of the specimen. Now, let's quickly look at the concept of strain. Assume a rod that is under a constant force of F. Due to the elastic properties of the materials, the length of this specimen will increase a small amount of delta L from the original length of L. If we divide the change in length by the original length, we get a unitless quantity known as strain. We use the Greek letter epsilon to show the strain. As the strain value is normalized by the original length, strain is defined as relative displacement. This type of strain is also referred to as a normal or longitudinal strain. Stress and strain are related to each other based on Hooke's law. This law is also referred to as constitutive law. Sigma is equal to E times epsilon. E is the elasticity module, also referred to as Young's modulus. This is a linear relationship between stress and strain, similar to the relationship between force and displacement in a linear spring. So far we have covered the most basic concept of stress and strain. There is another type of stress known as shear stress. Shear stress is caused by a force tangent to a surface rather than normal to the surface. Similarly, shear stress will cause shear strain. Shear strain will introduce distortion or angle change in the material rather than a change in length. Shear stress, usually shown by the Greek letter tau, is the force divided by the area. We use the Greek letter gamma to show the shear strain. There is a linear relationship between shear stress and strain similar to what we have for normal stress and strain. The modulus used here is shown by the letter G and is called the shear modulus. After understanding the concept of normal and shear stress and strain, we will go deeper into the concept of stress and strain. After going through this process, we will learn that stress and strain are not scalar quantities and Hooke's law in general terms is more complex than presented thus far. If we take a very small square section of a random object, in general, there are forces applied normal and tangent to all the sides of this square. The directions of these forces are shown using the subscripts x and y, which are our coordinate system. The delta sign used before each force shows that these are very small forces applied to the small section of the material. If we divide the forces on each side with the area they are applied to when assumed the size of the square approaches 0, we can calculate the normal and shear stress applied to a point in a random object. This can be shown mathematically by calculating the limit of the force divided by area when the area approaches 0. Therefore we will have one normal stress and one shear stress on each side. To satisfy equilibrium, the opposite sides have the same stress values. In this context, stress is not a scalar variable anymore. It is, however, a tensor, which can be shown using a matrix. As we described, the stress tensor can be shown for a two-dimensional problem using a matrix with diagonal members being the normal stress values and the off-diagonal terms being the shear stress values. This arrangement would form a 2 by 2 matrix. Similarly, we can define a matrix that shows the strain as a tensor. Diagonal terms are the longitudinal strains and off-diagonal ones are the shear strains. For mathematical reasons, we divide the shear strain values by 2 in the matrix. We can expand this concept to a three-dimensional cubic element with 6 sides and therefore 3 normal and 6 shear stress components. We can write all these stress components in a 3 by 3 matrix. Similarly, we can form a 3 by 3 matrix of strain with values of normal and shear strain in different directions. In general, due to static equilibrium and symmetry, all the off-diagonal terms, or in other words, the shear stress and strain components are equal in pairs. That would simplify the stress and strain tensors. This simplification helps us to write the constitutive law in a matrix multiplication format. In this equation, the strain values are presented in a vector format at the left side of the equation and can be calculated by multiplying a 6 by 6 matrix and the stress components written as a vector. This matrix is known as the compliance matrix. We have written the components of this matrix in terms of Poisson's ratio. Poisson's ratio, shown here with the Greek letter nu, is a material property that depends on Young's modulus and shear modulus. Thanks for watching this video. Hit the like button and subscribe if you liked it. Please also leave a comment and share your opinion.